Hi everyone, my name is Amanda. I am a climate defender organizer with Penn Environment. I just want to thank you all for coming to our Climate Action Expo today. Please check out some of the tables upstairs. There's also going to be some more presentations later in the day in this room and also down the hallway in another classroom, so definitely check those out. And also down in the south parking lot, which is right down the hill, we have some electric vehicles on display. Some dealerships are there for you to check out their electric vehicles, also some electric bicycles and things like that. So totally check those out as well. But right now, I want to introduce our first presentation of the day. Noel Smith is going to be giving us a presentation on understanding climate change. He is the lead for the Citizens Climate Lobby in Delaware County. He is also an executive director at JP Chase and has a bachelor's degree in civil engineering from Penn State, a master's in information technology from Drexel University, and his master's degree in candidate in sustainability from Harvard University. So yeah, without further ado, Noel Smith.
Thank you very much, and thanks everyone for coming today on, I guess, a very important weekend before a very important election. I appreciate you spending the time to learn a little bit more about climate change. And what I'll do when we go through the presentation today is if you have any questions, you're more than welcome to ask them as we go along and make it interactive. And I want you to come away with an understanding of what it is and what you can personally do to help with the situation that we find ourselves in. I'll introduce myself a little bit and why this is important to me as an individual and a citizen and a parent. I started to get interested in this topic probably 12 years or so ago, and there was a lot of debate in the environment, in the press, on TV, mostly cable news, and so you had these seemingly two sides of a debate. One said, yeah, we've got a problem. The other said, no, it's not so much of a problem. So I decided to buy a textbook on climate science and just determine what's real and what isn't. You know, my intuition was proven right. So I read a climate science textbook from cover to cover, and being an engineer, I actually found it really interesting. So I'm going to tell you a little bit about what makes me up. It did confirm where, what was real and what wasn't on the topic. So then I said, well, that's great. Now it's really something that I think that I need to address, and it kind of weighed on me. And the way that it weighed on me was I have 3 children, and I was a younger parent at the time, and I always thought about their future and what world I'd be leaving them. And so the thought I had was I actually imagined the conversation that I would have with my future granddaughter, my 8-year-old granddaughter. It doesn't exist yet. I have no grandchildren yet. But I actually imagined the conversation with this young, smart child, and she asked me a question. She said, Pop, if you know, what did you do about it? And so that's what kind of set me on this path to do something about it. And so I started. I got solar panels on my house. I felt pretty good. And then I found an electric car I could drive. That felt good. And I compost and I recycled and I cut my energy use, and I did all of those things. And then I realized that won't actually matter. I'm the only one that does that. So that I was kind of actually a little bit distressed about it. There's nothing. I felt like I personally, while those things that I do are good and they help, those by themselves wouldn't solve the problem. And so someone introduced me, I think about 3 years ago, to an individual from the Citizens Climate Lobby, and introduced me to a compelling plan that actually takes a systemic view of the problem, and they actually have a solution that we're trying to get our Congress and other Congresses of the world to take up. And we're going to talk a little bit about that at the end, but it's effectively, and actually we have an economist who's coming in after me to talk about carbon pricing and what that means. But so we will talk about it at the end, but my talk is mostly about climate change and helping folks understand it. Like I said, I'm going to go ahead and allow us to be interactive. If you have questions, I'll encourage you to go ahead and ask them. And I have a question for the audience first. Has anyone heard of the Citizens Climate Lobby? You have? And you have, okay. Well, you answered first, so I'm gonna give you a piece of candy if that's okay. I hope I don't hurt anybody when I do this. So that's how it works. If you participate, I'll feed you Reese's that we had left over from Halloween this week, so. All right, so go ahead and ask questions as we go. What I'm gonna talk about today is the role of the atmosphere. I'm gonna talk about, is climate change real, right? And so guess what? I'll probably tell you that right now. Yeah, it's real. But we're going to go ahead and talk about some of the supporting evidence that to go through that. We're going to talk about humans and their impact to climate change and modeling. And so we now have ways to model what climate change looks like, and that helps us answer questions like, what does the future hold? We're going to talk about that. And then we're going to talk about some ways that we can do something personally to help, and that's what really today's about. So this is a great picture. I love this picture. This is a picture from Skylab of the shuttle as it's entering the atmosphere. Okay, and what I like to reflect on this is that our atmosphere that keeps us at the temperature and the livability that we have is very thin, and it's almost fragile if you look at how thin it is. And the importance of that thin layer of atmosphere, the thin layer of gases that does its job to kind of protect the Earth. This is the temperature on Earth, and you can see in the middle it's a little bit warmer than it is up in the top and the bottom, but generally it's between, I think the Earth's average is somewhere around 55-ish on average in general. Probably it averages maybe 70s in the middle, 70s or 80s, and it's like 40s and 30s up in the north. But the net effect is our entire planet is generally livable. Everywhere that you could go, there's human beings and animals and biodiversity that live there. And so that's, there's something that kind of makes us that. So if we look at the closest celestial body to our planet, it's the moon. And you can see the temperature on the moon on one side where the sun is hitting it, it's almost 200 degrees Fahrenheit, not so livable. And then on the other side, it's minus 300 degrees Fahrenheit. So again, not so livable. And so there's really the difference between our rock and that rock is this thing called the atmosphere. Without this atmosphere, the Earth that we live on wouldn't be habitable, right? So that's just kind of some basic understanding of what it is. And so how the atmosphere works and stays, keeps that planet that we have in this habitable zone is called the greenhouse effect. And what I'm going to try to do is just talk through this greenhouse effect in terms that you can understand and even take and explain to someone else. But all of the energy that we have on Earth, and that's what keeps us at this temperature, it all comes from the sun. The sun shines down on the Earth and emits energy, and some of that energy emits right back into space. It reflects off of things that are reflective, like clouds, ice, and other things would reflect that energy back into space just like it came in, right? Other energy that hits warmer or darker surfaces like ocean or land masses, that heats up those masses, whether it's the ocean or the land, they're heating up. And when they heat up, then they transmit energy back out into space. But there's a transformation that happens to that energy now. Now that it's coming out, it's converted into heat energy, which causes the emissions to go out in what's called long waves. It comes in short waves, it goes out in long waves. And so now, when it goes back through the atmosphere, those long waves, some of them are reflected back towards Earth, and that's what the greenhouse effect is. Our atmosphere is able to deflect some portion of that radiative energy that is absorbed by the Earth and keep it on the Earth. And that's the difference between the moon and its uninhabitable conditions and the Earth and its very habitable conditions. And so I'm going to talk about the composition of the atmosphere to kind of, have you understand a little bit about what makes it up. And so the atmosphere is made up of gases. 99.9% of those gases are shown here on the left in the blue chart. So it's nitrogen is primarily, oxygen, that's 99% is nitrogen and oxygen. 0.9% of that is argon, and then this 0.1% is what we call trace gases. And in those trace gases, they're mostly made up of carbon dioxide. You can see that's almost 94% of those trace gases. And then there's a bunch of other ones, methane, nitrous oxide and some other ones that I can't say so other than the table below, but that's why we talk about carbon dioxide so much. The difference in carbon dioxide in those trace gases, just a little bit, makes a huge impact on our ability to store that sun's energy. And going back to the energy, thought, if you will, the more energy that we store from the sun in our Earth's atmosphere, the more warming that we have. It's really that simple. And so the chart here below, I just point out one thing. I've got the methane highlighted in red, and the reason I do that is each one of these gases also has a different global warming potential, and that is the ability to capture heat, the sun's heat energy, and keep it in the Earth. And you can see that methane in a 20-year period is 72 times more potent than one molecule of carbon dioxide. And so the other ones are even more so, but they're in more trace amounts. And so you can see methane's important too. Carbon dioxide is the big one, and that's what we talk about with the burning of fossil fuels. We emit carbon dioxide, but methane, if you know a little bit about how natural gas works and fracking, and the methane, which is natural gas that gets emitted into our atmosphere, you can see, even though it's much smaller in amount than the carbon dioxide, it actually has this kind of magnified effect, if you will. So I guess I have a question for the audience to see if anyone wants to earn a Reese's. When do you think, and again, you don't have to get the right answer, you just have to get an answer. When do you think we started to understand the atmosphere in terms that we just talked about, meaning understanding that there's this series of gases that make up our upper atmosphere that keep the planet warm such that we can live in it? When in scientific history do you think that occurred? Any guesses? Or if anybody knows it? Yes, in the back.
50 years.
50 years ago. That's a good guess, but I'll throw this for participating. I'm trying not to hit you. Oops, sorry. 50 years. Anybody? Any other guesses? So that would be around, I guess, mid to late 20th century. And you have another guess?
So I thought ExxonMobil knew about the precariousness of things in the 60s, but that's not your direct answer.
60s is another good guess, yeah. So.
But I don't want to Reese's.
You don't want to reach?
Thank you.
Okay. Well, I'll give you the answer. It was actually the 1800s. So we've known about this for some time. In 1824, scientist Joseph Fourier discovered the greenhouse effect. In 1862, John Tyndall discovered that certain trace gases trap heat. And in 1895, Sir Bente Arrhenius discovered the infrared absorbing properties of the greenhouse gases. So in the 1800s, we actually had the answer. Our scientific community knew what was going on and what would go on in terms of how the climate system worked and how it trapped gases. This is a scientific, I guess, certain fact. It's been in our journals for some time. Our scientists have known that. And to your point, ExxonMobil has known that because they had climate scientists in their organization as well. And so anyway, the point is we've known this for some time. This is not new science, if you will. So I'm going to talk about some observations in the atmosphere. I've got 4 charts up here, and these are direct observations. These are measurements that scientists have been taking over a period of time since, I guess, the beginning of the 19th or the 20th century. So our northern hemisphere spring cover has been decreasing over time. That's the first chart on the top left. The second one on the top right, the global ocean heat content has been rising. On the bottom left, it shows the sea ice extent, and so this is the summer sea, I guess in September, they take a measurement to compare September to September, so this will be the end of the summer, and you can see that's dramatically decreasing, and then the global sea level, the mean sea level has been rising since 1900. Again, these are direct measurements of what's going on in our environment as well. So there's some compelling evidence that something's happening. And so what this chart shows is, first I'll talk about the picture of the Pacific Ocean and that little dot that's in the middle of the ocean. That's the Mauna Loa Observatory. It's in Hawaii. It's at the top of a mountain in Hawaii. And the reason they decided to do the observations here is that this is a place where the atmosphere is well mixed. So it's not near any industry, and you can get a really nice sample of what does our atmosphere look like from and they're measuring the amount of carbon molecules that are in there. And again, I talked about earlier how sensitive our climate is to these molecules. So you can see the chart on the top left shows that since they began these measurements in the 1950s, every year the amount of carbon dioxide in parts per million has raised. In fact, it's not even a linear model. It's kind of it increases every year, the rate at which we're increasing carbon dioxide in the atmosphere. And I have another question for the audience, and you guys can jump on this one, but you can see that line goes up and down, right? Every year, it goes up, goes down, goes up and down, and it kind of has a pattern. Any thoughts on what that pattern might represent? Why does it go up and down every year? Yes? No.
Using heating,
Using heating.
heating and air conditioning.
I'm gonna throw one at you, hopefully I won't hurt you, buddy. Oops, good guess. It is not the right answer, though. It's not because of heating, it's a good guess.
But yes.
Any other thoughts? What happens every year? We have seasons, absolutely, great answer, love that. So we have seasons. I'm gonna throw, yeah, you got it. Good catch. So the seasons change, and what happens in the seasons is, in the spring and summer, all the leaves pop out, and they capture carbon dioxide, and they put it in the ground. So if you ever heard about carbon sequestration, the natural process of carbon sequestration is, it's what happens every year when we have all this vegetation and it absorbs the carbon dioxide from the atmosphere and it stores it in the ground, right? And so it's actually a system. The fossil fuels that we burn today, they were solar energy that were stored in leaves and plants and animals and were buried in the ground and compressed, and then they became fossil fuels. So fossil fuels is just stored solar energy. So all of the energy, so the earth is breathing is that's kind of the, how I like to describe it. Every year is breathing in and out, and that's what that chart represents. And as it absorbs all of that carbon dioxide in the northern hemisphere, when we have summer, spring and summer, it's absorbing all the carbon dioxide and actually reduces the carbon dioxide molecules in the atmosphere. And in the winter, all the leaves fall down, and so we're no longer absorbing them. And so the emissions that come out then allow it to go back up. And so it goes up and down every year. And it's just the seasons that we have. So I find that to be fascinating. And I see that as the earth as a kind of this living organism that's breathing on an annual basis in and out. And so that's the measurement of the carbon content in the atmosphere. And down on the bottom, right below it, is a similar graph that goes up over similar periods of time where you can see the burning of fossil fuels in the industrial age really kind of taking off, and in the 40s and 50s is really where it kind of started to just take off like in a dramatic fashion. And so the pre-industrial concentration of carbon dioxide in the atmosphere was 280, and the current, and as of a couple days ago, I guess, was 406. But the record was 412 in May, right? So we now know why it went down, right? We had summer in the northern hemisphere, but it's going to go back up in I guess next May it's going to be probably my guess is going to be 414, right? It's about how much it works every year. And so there's a tight correlation. So I'm kind of building the case again. We had observations. Now I've got these correlations. There's a tight correlation between emissions and the measured carbon dioxide in the atmosphere. So this is what it looks like over millennia. You can see this is the carbon dioxide concentration content over 400,000 years, okay? And that represents our ice age cycles, okay? And the question I have, this is a bonus question. Does anyone know how we can measure the carbon dioxide 400,000 years ago? Yes.
I'm cheating because I have a science degree, but basically they take these huge ice cores, they bore down into the ice with a drill about this big around, drill down into the bottom of these really old ice sheets, and then they measure the bubbles in the ice. That tells you the concentration in the atmosphere.
Bingo, that's exactly right. There's your candy. Awesome, thank you for that. It's a perfect answer. I couldn't explain it any better. So we actually know how much carbon dioxide was in the atmosphere going back even, I think they actually have much further than 400,000 now through other methods, but through the ice core method, it's 400,000 years. And you can see it reflects back and forth. And it's been between like maybe 180 to 280, or you could say 200 to 300 has kind of been in the normal range, if you recall. Everyone talks about natural cycles. There are natural cycles that change the carbon dioxide that's in our atmosphere, and they have to do with, and I didn't put charts in on this, but as the sun and the earth interact, there's different angles of inclination of the earth that happens over millennia, and because of that, it changes and going right back to solar energy. If you go all the way back to that chart at the beginning, the amount of solar energy that comes into our planet that gets absorbed into this greenhouse layer, that's what determines the temperature of the planet. And so that's what determines our ice ages. And so the interesting fact I'm going to talk about before I get into where we're going is that range of, like, let's say 200 to 300 parts per million, the difference in that 100 parts per million is the difference between an ice age or not, okay? Just to tell you how sensitive that is, okay? So with that in mind, now you can see if you bring it all the way back to the right of that chart before it spikes up, we were at kind of the top of the period. It would be like a natural warming period in the cycles of ice ages and not ice ages. We would just be starting to go down that path over 100,000 years of going into the next ice age. That's where we are on the geological time frame. But something happened. Instead of going back down, it took this dramatic shift up in a very short amount of time. And it's, like I said earlier, it's at 406 parts per million now. Never been seen in the history, or history is the wrong term, I guess, but in the known existence of humankind. We've never seen a concentration of carbon dioxide this high, and you can see it's happened very quickly. The top chart shows just the last 1,000 years, and you can see it's been rather stable until something happened around 1800, and then it started to kind of peak right up. So that's how unnatural what's going on is as far as the carbon in the atmosphere. So this is, now we're getting into the questions, is climate change real? And we're going to focus on average temperature. This is a chart of the combined land and ocean surface temperature over time. And again, you can see in the 1900s, it starts to go from like a flat line to an upward inclination. And so we're going to go and just look at this hypothesis. The hypothesis is that the global average temperature has increased over the past about 100 years, right? So how would we prove that or test that hypothesis? There's different statistical techniques that you use, but really you're just looking at trends. Is the trend, is it zero or non-zero, right? That's number one. Is it, going up or down? Is the mean at the end different than the beginning, right? So if you took a mean at the end of our 100 years and at the beginning, is there a difference in it? And is that change more than kind of the natural year-to-year variation? So that's the statistical look at what this is. I'm trying to keep this kind of simple, but this is the chart of global average temperature over about 100 years. And you can see from this chart that, there's positive inclination of the trend. You can see that the mean on the far right is different than the mean on the far left. So it's bigger than the anomaly. So clearly the answer is yes, the climate change is real. Something's happening. I position a whole series of observations and kind of the hypothesis of why it would occur with the molecules of greenhouse gases that are there. And now we actually proved this hypothesis through direct measurements. And so in 2013 report so is anyone familiar with the Intergovernmental Panel on Climate Change? Right? So there's a body of scientists globally that have been working on this problem for decades now. And they've concluded that warming of the climate is unequivocal. And since the 1950s, many of the observed changes are unprecedented over decades to millennia. And that's what we were talking about all along. But these are the smartest and most esteemed scientists in the world have come up with this conclusion. So now we want to look at the future. So we understand the past. We want to understand, well, what does this mean for us going forward? And so these climate scientists are building or have built climate models to understand the climate system. And so what I've pictured here is the Earth, and over top of that Earth we have these grids. And these grids are all interacting. And this is how we built computer models of climate systems. And so in each one of those grids interacts with the grid next to it. And the inputs and outputs of those grids are the Earth systems. And the Earth systems include things like the evaporation, volcanoes. It includes the rain and the seasons and the sun's energy that comes in. And they modeled as many things as they could, and they put into this model to understand all the Earth's systems. And if you go back to what I talked about earlier, we've understood the Earth's systems since the 1800s, and they're building on that as they go, and they keep adding more and more to this model, and the models are becoming more sophisticated. And this is kind of a picture of the advancement of the climate models. If you went back probably into the 1970s or so, that top left one where remember that grid that I showed you on there? All those boxes that were covering the Earth? So that top left grid is a 200-kilometer box, right? If you just, and that was as granular, as powerful as the most powerful computers in the world at that time could only analyze a box that was 200 kilometers on its side. And then the one on the right is 50 kilometers. And so we're getting more granular and a better understanding of that. And then the one on the bottom left is 25 kilometers. And so as our compute power goes up dramatically, and we have these supercomputers, we're able to get very close. In the bottom right is the actual observation. And so you can see now the actual observation of that climate, that weather system that you see on the bottom left is almost identical to the bottom right. So we've understood this now to a high level of certainty of how the climate system works. Okay? And so what I'm going to show you is another hypothesis we want to work with. The hypothesis is that human activities through the burning of fossil fuels are driving climate change. So that's our hypothesis. So we want to run these computer models that look like our real Earth, right? So we just talked about building those computer models and all the inputs that we do it. And then we're going to run those computer models for an Earth without anthropogenic greenhouse gases. So we're going to run it with us and without us, as if we weren't here, right? And we're going to see how the model changes to understand it. Okay. So this first graph shows many simulations of that model with human factors, and you can see the model is the red line, and the observations are the black line. And you can see they're pretty much in parallel, right? Our computer models are directly correlated to our observations, if you will, except for one period of time. And I don't know the answer to this, I just have my own speculation, but at some point right around the late 1930s into the 1940s, something happened that caused the observations to be different than the model. Any thoughts on what that might be? I have a thought.
World War II.
Yeah, that's what I think too, right? So World War II happened, and with that was a dramatic increase in human activity and fossil fuel burnings and atomic bomb blowing up. So lots of things happened. Here's your candy for that. Thank you. Awesome. So my speculation, I actually have nothing to prove it, but I think that the 1930s, 40s anomaly in the observation in the model is probably something they didn't model, which was World War II. But let's go through now. I'm gonna pull up the next slide, and it's gonna show, let's pull the human activity out of the model and see what happens. Oops, yep, there it is. So this is the model without human factors. Now you can see the black line, which is our direct observations, is different than that blue line, which is what our model says. And so the conclusion is we can only explain the observational record, what's really happening, if we include human inputs to the atmosphere. Okay? Does that make sense?
Yeah.
And this is that model applied across the world, and you can see it's similar. No matter, we do it globally with land, with ocean, with both. We do it in Africa, we do it in Asia, we do it in South America, we get the same answer. That the only way to show the difference in our models and the observations is if we say that human activity has been the influence. And so it's been detected. We've shown you slides on the warming of the atmosphere, the warming of the ocean. It's changing the global water cycle, and I'll talk about that in a little bit. The snow and ice reduction that you've seen, sea rise, and we've seen climate extremes as well. And so the 2018, that IPCC group of scientists put out a new report this year, a few weeks ago, and they concluded that human activities are estimated to have caused approximately 1 degree Celsius in the global warming above pre-industrial levels. And again, that's from direct observations. So let's talk about direct observations a little bit. This is a fun slide that we put in here, but some people say that scientists can't agree on the Earth's temperature changes, and that's true. And this is a depiction of their disagreement, just so you can see. They are radically not that different actually. So while our scientists do disagree, and they will continue to disagree, that's what they do, they're scientists. And so this is, when you hear folks say that our scientists are not sure, there's some level of disagreement as to the amount of warming, this is what we're talking about, right? So there's a lot of reasons why that occurs, but basically they're scientists and they're all trying to find the right answers to the problem. So using those models, so now we've determined that we can model it and that the models are accurate. And so now we are no longer looking in the past, we want to look in the future. We said, let's use that model to see what our future might look like if we throw some different scenarios in. And so the red line is called a high CO2 future, okay? Then that's what they call it in the IPCC. I actually call it business as usual. This is actually the path that we're on right now, unless we change something dramatically. And so the bottom one is switch to mostly renewables, right? So that's like if we stop right now and we just pivoted and switch to renewable, non-carbon based energy, or we bury that carbon in the ground somehow. If we did that right now, you could see that we could stabilize somewhere above 450 parts per million. Still not great, but we come back down and we stabilize somewhere just below that. So we have a chance for a livable planet. And then they got the one in the middle, and I call that sum of each. That means we took action pretty soon, but it's really hard to change the entire world's economy at once. And so we're going to probably, if we do our best to solve this problem, we might get lucky and land up somewhere of each. I don't know, but we'll see. And so what does this look like? This is the global surface temperature of the Earth. And I'm going to qualify that a lot of the charts that the IPCC did were within a context of what happens between now and 2100, because people could kind of comprehend 2100. But just keep that in mind, 2100 is not stopping there. So a lot of the charts I'm showing you show what's going on between now and 2100. But according to this model, that business as usual scenario that we showed shows the global average surface temperature changing by somewhere between 3 and 5 degrees Celsius. And that's a fairly dramatic change in temperature. And then if you see the kind of the best case scenario is somewhere down around 1.5 degrees Celsius. You hear a lot of talk about trying to get to 1.5, but to get to 1.5, again, you have to pivot now. Time is of the essence. And so again, I'll say just to set expectations, it's likely we land somewhere in between if we do our best. But hopefully that's something we can affect, and we still can affect it. This is a chart of warming and what the Earth looks like between, and now this one's in Fahrenheit. Hopefully it'll give you a little bit more perspective for our case. But the one on the left is the best case scenario. This is the temperature change in Fahrenheit in most land masses. We're looking at 5 degrees maybe in Fahrenheit temperature change. And if you look at the right one, our land masses go up anywhere from, it looks like 9 or 11 degrees Fahrenheit to 15 or even more. You can see the Arctic is that deep red. So you're talking about 15 degree Fahrenheit change in the temperature of the Arctic. And so you know what will happen when that occurs as well. And so warming from anthropogenic emissions from pre-industrial to present will persist for centuries to millennial and will continue to cause further long-term changes in the climate system. This was out of the latest report from that international body as well. Some perspective on ocean rise. This shows, again, by 2100, we're going to have ocean rising somewhere between 0.5 meter and 1 meter. Again, between maybe 1 and 3 feet between now and 2100. Sea ice extent is pretty much, the summer sea ice extent is pretty much going to be gone. I find it hard pressed to find a scenario that actually gets us there. I know this is the best case scenario will allow us with some sea ice, but it's pretty much we're going to be without sea ice in the September timeframe going forward in this view. So the answer is that the future will be warmer. The estimated global warming is currently increasing at about 2 degrees Celsius per decade due to past and ongoing emissions. And here's a strong statement that they just put out in this report a few weeks ago. Limiting global warming to 1.5 degrees Celsius would require rapid and far-reaching transitions in land use, energy, industry, buildings, transport, and cities. So that's a pretty powerful statement. So this is a body of scientists that are very conservative about the statements that they make. They never want to overstate something that they can't prove scientifically. So for them to make this statement is really, they're trying to help help all of us understand the urgency of what's going on. So let's do some perspectives. I always like perspective. I talked about, 2100 in a minute, but today you can see where we're at on this chart. This is over the last 1,000 years and the temperature of the planet. You can see again, it's been pretty even keeled up and down a little bit over the last 1,000 years until, the late 1800s, 1900, and then it spiked up, right, pretty dramatically. And so to finish this chart, the next generation, right, our children and our grandchildren are projected to be somewhere in that upper range, again, depending on the decisions that we make today. And you can see it can get pretty dramatic. We're looking at temperature swings of 2 to 6 degrees Celsius in, again, our grandchildren's lifetime. So it's a fairly dramatic perspective to see. This is perspective on ocean rising. Again, I talked about 2100. Why 2100? I don't know. They picked that. So let's look at 2300 if you just want to get some perspective. So 2300, if you look at the history of the country that we're in, I guess we're about 250 years old. Doesn't seem that long ago. So just let's go 250 into the future and see what the oceans might look like if we don't take action today. 10 to 16 feet raise in ocean depth is fairly dramatic, right? You're talking about, Miami doesn't exist anymore. Like cities that we consider just where we're at today actually are not livable. Actually, most of our coastal cities wouldn't be livable or even exist in 2300 if we continue down the path we're on now. So it's a fairly dramatic statement to say we're going to have this, and the science again backs this up. I'll just qualify this chart here a little bit and saying that those scientists that put this together have been on the conservative side of what the impacts are be. In fact, we're learning how to measure these. It's highly likely that they got this a little bit conservative, and the 16 is probably the lower end of what might happen. So you're probably looking at oceans that are much greater than 16 feet. And it's still going up from there. Again, we picked 2300, but it's not stopping there. It's going to continue to rise unless we do something about it. So let's talk about extreme weather events and can they be tied to climate change. This is 2017 billion-dollar weather and climate disasters that occurred within the continental United States. And, you can see there's a bunch of them on there. Some of them you probably recognize, the hurricanes that are down at the bottom. You see some wildfires that are occurring out west. Tornadoes occur. Flooding. Flooding is probably one of our biggest impacts here in the Northeast. If you haven't been kind of picking that up, but the rainfall, as the earth warms, you can just understand evaporation. More moisture goes into the atmosphere, and that moisture falls. And again, I'll go back to the sun's energy. All of that is stored energy from the sun as that water vapor goes into the atmosphere. It's actually, these are energy systems. That's why you see tornadoes and hurricanes like they do. They're actually expending the energy that comes down from the sun. So you can see in the Northeast, we don't have any billion-dollar disasters in 2017 on this chart, but we've had a lot of flooding issues that occurred. There was an issue with Ellicott City, Maryland. Does anyone recall that disaster that occurred? It actually occurred twice, I think, in the last decade, where they had a rainfall so dramatic that it pretty much wiped out Main Street of Ellicott City, Maryland, twice in the last 10 years. And they call that a 1,000-year storm. And if you just look at, well, what does a 1,000-year storm mean? A 1,000-year storm means that statistically, that should occur once in 1,000 years. Well, if that happened twice in 10 years, it tells you there's something probably going wrong. So all of our, so I'm a civil engineer, I did that for the first 10 years of my career, but all of the regulations that we have are based on things like 100-year storm, 500-year storm. All of our civil systems, our roads, our bridges, our sewer systems are based on 100-year storm, 500-year storm. all of our flood charts are as well. Our flood insurance are based on those things. Well, if those metrics or if those measurements change, which they are, how do we design systems that to account for a changing world? We measured 100-year, 1,000-year, 500-year storms through historical records, and so they're changing dramatically now. So do we re-baseline on what's happening now and say, well, let's remeasure what a 500 and 1,000-year storm might be and start to build systems, civil systems that can account for those, right? The problem with that is it's still changing. It hasn't actually baselined and stopped changing again. So everything that we built in civil society was dependent on a stable environment. And that's how you connect that temperature and that CO2 to everything that we have going on in human civilization today. So anyway, I'm going to go to the next chart. And again, 2017 was just a picture of what happened that year. It doesn't really mean anything by itself. So let's look at that same chart but thrown in a graph. So this is what that chart looks like over year over year. And you can see it's increasing. So our billion-dollar disasters are in fact increasing over time, and many of them are severe storms and flooding and things like that. So there is evidence to show that it's coming. And so the question then, right, can extreme weather events be tied to climate change? That's what they're trying to answer. And so the answer is a little bit more complex. We can't just say, yeah, that hurricane was caused by global warming. We can't say that. Hurricanes occurred before and they'll happen after, there's an after. But what we can say is that the odds of a particular type of event are different with and without climate change. And that goes back to what I was saying about 100-year, 500-year, 1,000-year storms. Why are they occurring so frequently? Those things, it doesn't rain because of global warming, but boy, it can rain more intensely. And we don't have hurricanes necessarily because of it, but boy, they can be more impactful because of it, and the odds of those things happening are increasing. And so we're kind of, they call it, we're loading the dice, if you will, to have more of those types of storms. And the trends in intensity of some of the climate weather extremes have been detected over spans of which we've had about a half degree warming. So the bottom line, and I'll just read kind of the underlying line, is global net human-caused emissions of carbon dioxide would need to fall by about 45% from 2010 levels by 2030 to reach net zero by 2050. And so that is, we talked about 1.5 degrees. And remember that happy path I showed earlier, the green line at the bottom? If we wanted to hit that one where we actually leveled off the atmospheric impacts, we would have to hit a 45% reduction by 2030. That's pretty dramatic. So we got to change now. And that means we got to get net zero by 2050. So here's some implications for the warming world. Oceans, the oceans are rising. It's getting warmer. We're getting more acidic in the oceans. Again, that has a change to shellfish and has an impact to coral life. And just some perspective on coral reefs and what they do is, I think it's somewhere around 30 to 50, and I should go look at this to get the number right, but a large percentage of the fish nurseries in the world are in coral reefs. And so you're impacting the global food system if you remove the nurseries for 30 or 50% of all fish life. So it's a pretty dramatic impact. It's not just tourism that gets impacted by coral reefs. It's that biodiversity that occurs. So land, we got this desertification, wildfires and droughts. Weather, we talked about rain intensity, cyclone intensity, increasing droughts. And then human health is another one that we don't talk a whole lot about, but there's an increase in heat-related illness and death. Vector-borne diseases. It was the Zika virus that occurred and it started to move north. Well, guess what? As the earth warms and mosquitoes, they're carriers of these diseases, and as their blood temperature changes because of the increasing activity, different viruses come into play as that happens. And so there's a direct correlation between the diseases that are carried by mosquitoes and the temperature of their bodies, and their temperature of their bodies are based on the atmosphere. Air quality degrades with the warming earth, and food and water shortages, and climate refugees. There are climate refugees today, and we're not really talking about that today, but that would be a whole other topic. But there have been climate extremes that cause desertification and loss of arable land, and people move to cities and wars happen. So Okay, so what can we do about it? First of all, is you want to encourage action at all levels. That means your state, your local, your federal, all levels of government should be involved in solving this problem. And you personally can solve it as well. Reduce all waste is something that I've kind of taken personally. Everything we do, everything we use takes energy, and it all contributes to emissions somewhere. I always purchase the most efficient machines for what I do. And that goes to the next bullet, which is think long term. Don't just think of the price of the product today. Think about the price of the product to run it over time. You'll find generally that buying the most efficient machines will not only save you money, but it'll reduce the impact on the planet. Eat less red meat. I like red meat too. I do eat less of it now because of this, but again, red meat takes more energy to produce, and that's what it's really just about, is energy. Buy local where you can, educate yourself, vote, which is very important. Keep that in mind when you do it, and plant a tree. Is something you can always just do, but I talked about carbon sequestration earlier. That is the Earth's method of putting carbon back into the ground. So you can really take that. And I'm going to hit on a couple things at a really high level and then introduce our next speaker. But I mentioned that I'm with the Citizens Climate Lobby. That's not my day job. My day job is I work in technology for a bank. But my side hobby here is trying to solve climate. And the Citizens Climate Lobby has a fairly simple solution to a very complex problem. I'm going to introduce it to you just briefly. But what we do is the first best step is we put a fee on fossil fuels at the source of extraction, okay? And the really good news about that is we actually have this number today. You can be sure that anybody that's extracting fossil fuels from the ground, they know exactly how much carbon is coming out of the ground. So we know this answer and we already do it. So the first one's easy to do. The second part of the plan is we take all of that revenue and we give it back to everyone. Guess what? Our government's really good at collecting and distributing money. So number two is really easy to do, right? So far we've got a really complex problem and there's a solution that's not that hard. We've figured out how to do these two things. And then the third part of that is what's called a border adjustment. So as goods come in and out of our economy, we don't want to punish manufacturers who are paying for the price of carbon and incent ones elsewhere that are not paying for that. So we adjust it on the border. And guess what? We're getting really good at tariffs now too. So there are ways to solve all of these, and it's very, this is actually easy. The hard part is making it happen. But let me just tell you about this carbon fee and dividend over 20 years. We talked about 2030, we needed to reduce emissions by 45%. To show you how hard this is. If we put this rising price on carbon, first of all, on the kind of over on 10 o'clock on this, household dividends would be about $400 a month. Right? So you would get a check in each household, average of about $400. We would reduce the greenhouse emissions by about 50% in 20 years. 2.8 million jobs would actually be created because of this. The GDP would grow. And my favorite bullet out of all this is we would save 250,000 lives due to the health impacts that I talked about earlier as well. So there is a plan, and really the hard part about that is getting our governments together to go ahead and solve that problem. So thank you for your time, and are there any questions before I turn it over to Tal? Awesome. Oh yeah, go ahead.
So you talked about a 45% reduction in CO2 emissions over the next 20 years, whatever that is. Well, how much of that, if any, will happen through market forces, and how much of that is going to need to be driven by advocacy?
So the question is, we need to reduce 45% of the carbon emissions in the next generation or so. How much of that is going to be through market forces, and how much would be through advocacy? So advocacy, so the way I'll answer that is we need market forces to do that. Absolutely. Advocacy alone I'll give you my opinion now, is going too slow, right? We have a lot of advocates. We're here in the room. I go to events all the time, but I talked earlier in the presentation around my own personal challenges to reduce my carbon footprint and how feeble they were in the context of all of it, because we need systemic action, systemic change. And so what I would say to that answer is we actually absolutely need market forces to do this, because we need systemic solutions to a complex systemic problem. And without the market shifting, because our entire economy globally now is based off of burning carbon, right? It's extracting and burning of carbon. And so that requires a systemic change, and that means we need market forces. And the best way to, and this is a great tee up, so thank you for your question, but the best way to move markets to do something that you need it to do is to put a price on something. And pricing is the way to do it. By pricing carbon, you move markets. So, thank you. Okay. Oh, yeah, question here.
Comment and question. I guess more about the previous slide, if that's easy to
Sure.
go back to.
This one?
So thanks for your presentation. I agree with everything. Actually, there's one slide earlier. Sorry.
Yeah, this one.
So you're right. The government's created, taxes, tariffs, distributing. I think what's missing from this, and I guess I got pitched on this concept recently. I'm sort of tangentially involved with Sierra Club's Right for 100.
Oh, great.
I'm on a liquidity space. So what's missing from this, to me, is an investment in renewable energy technologies.
Sure.
If you're gonna, whether it's cap and trade or some other economic model where you're placing the fee on fossil fuels, which is long overdue, all that revenue can go into incentives, whether it's purchasing electric vehicles or businesses to go renewable energy 100%. Smart grid. I mean, all the technology that's going to be required for this rapid transformation of infrastructure. So it just seems like the massive distribution to people will be unpalatable to at least 40% of the population anyway, politically, should be invested in. I mean, it seems like not in the last 2 years, but previous 8 years, fair amount of progress on renewable energy, in part because all these policies are put in place. But you need the investment in the technology to do it. So that seems, to me, a huge deficiency in that.
So great. So I'll restate the question a little bit. So everyone's sure. Yeah. So the question is why wouldn't you? If I don't phrase it properly, just correct me. Why wouldn't we spend the dividend money on incenting renewable energy and other means to move us even faster? Did I get that about right?
Yeah. And whether incentives, investment in technologies,
Yeah.
to both individuals, companies.
Yeah. But it's about taking that dividend and investing it in ways that helps us to get there faster.
Yes.
Right. So first of all, personally, I agree with that 100%. And I think that would be a palatable, move. And I think we would all agree that the faster we get there, the better. Why not use that money to do that? But to your point, I think we need legislation that'll pass. And so we've listened to many people as we develop the solutions. And we need both sides, if you consider us two sides of an aisle in this country. Some want big governments, well, I should say it that way, they don't want big. Some are, let's say, anti-government action or activity, and some are saying, hey, more activism. So we're trying to pick something that's palatable to many people, number one, and we get support from both sides of the aisle. And so we think this solution, as built, is gaining support from activists for moving forward on this and folks that are on the small government side. And the idea is that it's using the market to drive where to go. So that's what it is, number one. And number two, we also think that this stands alone, and you can layer things on top of this. So you can still have, even with this policy, if this is still in place, you could still have incentives that go on top of this. This could be a foundation to, you add incentives for renewable energy, you have portfolio standards, you can have electric car incentives, however you want to do it, they can all layer on top of it. So I do agree with you. I would love to see all of that revenue distributed in a way that further accelerates this, but we're trying to get legislation passed that we can get bipartisan support to handle. So I hope I answered some of your question and your concern. Thank you. And there was another question over here, I think? Yeah.
Good question. With fracking in the state of Pennsylvania, how much of a carbon imprint is that?
Yeah, so the question is about fracking and what's the carbon imprint. So there is a theory that says that natural gas has a lower carbon footprint than another fossil, than coal or what have you. And I guess that might be true for burning of natural gas versus burning of coal. But the extraction of methane or the extraction of natural gas through fracking actually allows a lot of a lot of the methane to just bleed right into the atmosphere. As you saw earlier in the talk, we talked about the powerful impact of methane as a very strong greenhouse gas. And so we don't, there is a case to say that they're burning the extraction as we do today, and burning of natural gas is not much better than other types of fossil fuels. But if I go back to like the carbon fee and dividend plan, that would, in the short term, probably incent some level of natural gas extraction versus coal and oil, but that too would fade over time as we go to 100% renewable. Yeah, sure.
So where are we on this carbon tax now?
Yeah.
I'm a little confused. Is there progress on it? Is there legislation?
There is not legislation in the United States of America to put I guess a national price on carbon. And I think our next talk is going to have, Tal, I think you've got a slide on this answer actually, like where we have it and where we don't. Canada just put a price on it right now, and if you saw that in the news recently, Canada has a price on carbon. We don't have a national price on carbon. We're working to do that. We're making progress, I guess, without legislation. I know there's a bipartisan group in Congress we're hoping works towards this. It's called the Climate Solutions Caucus. It's made up of 90 members of Congress right now, 45 from each party that we're lobbying them hard to push forward with this agenda. So we don't have it there yet. We're trying to make progress. And if you want to, upstairs we have a table. We ask you to write a letter to your member of Congress. We'll hand deliver it. So we're working relentlessly to try to bring it forward. You have a question here?
I do.
Yeah, go ahead.
I know this is really unpopular, and that's part of the climate problems, I believe. But I thought it was the IPCC or some important panel that said that animal consumption consists of the methane from animal consumption and all connection with that is more than all transportation combined.
Yeah.
Whether that's true or not, you know, we're growing grains to feed the animals, to eat, you know, to make us sick, make the waterways sick. So I would just encourage people, and I know you touched on it there, and I know you're also maybe, you're scared to get people running out the door and say, I'm not going vegan for the climate or for anything else, but it's to have a serious conversation. I feel this is where Al Gore fell a little short, that he just would not utter those words. We've got to stop raising and killing and eating animals. There's a cost to that, and we're bearing the cost.
So I'll bring it back to the science that we talked about earlier. I'm running out of time. So all the energy we have comes from the sun, right? We've established that, and the sun puts the energy in the plants, and if we could eat those plants, that would be the most efficient way for us to get solar energy. Because we need solar energy, right? We all want solar energy. The most efficient use or way to get our solar energy into our bodies is by eating plants. The least efficient is feeding it to certain animals that, you know, again, it's just like a machine, and it's there's less efficiency as you go down the food chain. It does cost a lot more to eat red meat, a lot, not even a little bit. Red meat is the most carbon-intensive meat that we eat. So if you do want to make a personal choice, there's a lot of information out online about that. If anyone wants to talk more about that, we can. But a personal choice you can make is to try to limit your red meat consumption, and that will make an impact. So thank you. All right, am I out of time, Peter? All right, so I will take any other questions folks have after, and I'm going to introduce our next speaker. We have Tal Lamb, he teaches economics at Squamish University, and he was the High Meadows Fellow of the Economist at the Environmental Defense Fund, and he has a master's degree and PhD in economics from Princeton University, along with degrees from Ohio State and the Shingle universities in his home country. And so I'm going to bring up his presentation and ask you to come forward.
He's got a new one too.
Okay. All right. I'll turn it over to you, Peter. So just give us 30 seconds to